Alright, so hello and welcome. We're going to take a look at yet another problem now. It's going to be expression add operators. LeetCode hard, presumably C++. I think we can get right into it. Jump right into it. How are we doing? Yeah. Given a string num that contains only digits and an integer target, return all possibilities to insert the binary operators plus, minus, and or multiplication between the digits of num so that the resultant expression evaluates the target value. Note that operands in the return expressions should not contain leading zeros. Okay, so numbers 1, 2, 3, target is 6, 1, 2, 3, 1 plus 2 plus 3, both 1, 2, 3, and 1, 2, 3 evaluate to 6. So only add, subtract, and multiply. Let's see, how many num consists of only digits? Num is between 1 and 10. Num is an array, a string of digits, and so there's only 10, which is nice. Excuse me, and the target is just any integer. Okay, so I think this is probably not too hard. This is a this is a depth first search. It's actually better than that. It's not depth first search. You can memorize this too. Yeah, so this is, do we want, yeah, I think I moved this over before for the SQL. This shouldn't be too bad. Probably can memorize this too, on a certain, yeah, you can memorize on the target number, and does that work? Let me think. You can memorize on a certain index on what all the possible numbers are, something like that. I'm actually not sure if you can memorize this. I thought you could, but I don't know about that. This might just be a strict depth first search. I'm thinking about it. This might be harder than I thought. Definitely depth first search. We can start with that, but 10 factorial is not too unreasonable for a depth first search. Yeah, it's not too bad. I'm just thinking, I don't know. A couple things. Only have 3 operators, and the resulting expression has to be the target value, not contain any leading zeros. Operands and the returned expressions should not contain any leading zeros. Oh, wait a second. Whoa. Between the digits. Oh, excuse me. So 1005 gives you an oh, I didn't think about that. Oh. This could be really awkward. So it looks like you could put, oh no. That's really awkward because we don't know how big could these numbers be. Well, 10 digits could be more than a billion, by the way. Well, every digit will fit into an int, or every number, but actually you need to evaluate each of these numbers. So that's maybe the first thing, is we could do a pre-processing step to get every number given an I and J range. We could just we can get the numbers that are there. That's probably the first thing we should do, is create that pre-processing step. That shouldn't be too hard. That's just, is that hard? That might be too hard. I mean, saves you a bit of work, right? Make that constant time instead of looping through. I guess it's not that big of a deal. It's just a few multiplications to get that number. Parse the string and parse out the integer. You could also build a table to do that too, pre-processing step there as well. I don't know if it's entirely necessary. Maybe you'd want to do that just so that way the backtracking here is not so bad. So the deal is you can get, the backtracking is kind of tricky. I'm wondering if we can optimize this. That's kind of what I'm looking for, is like a way, sort of. Memoizing with respect to the target is kind of meaningless though. That's kind of the problem. You can memoize with respect to that, but that's kind of useless. The reason why that's kind of useless is basically for each index that you can insert one of these three, the sub-expression to the right, the range from towards, from that index all the way to the right, that has a set of possible result values and the associated strings. And so you can return that, and then for each of those, if the value, either add whatever's to the left, add, multiply, or negate. So you would perform the operation, right, on sort of at each of these insertion points, from left to right. If that gives you the target, then that's a result that you want to use. And then you would add to your return vector that string that represents that sequence. The problem with this though is yeah, I mean, you could just do this recursively. Technically, you could use DP for this also, but you might want to go right to left. Actually, it's a little bit easier. No, left to right's easier, because you could build your integers as you go, as you loop through. So you don't need to do that, the whole thing I was describing. But still, you have issues of you want to, you can recur. I mean, you could do DP instead of recursively. I think recursively should work. Should be fast enough. Chance is not fast enough, but hopefully it is. Yeah, depth first search seems fine. I mean, what else are we gonna do here? Only issue though is that 3 raised to the 10th is a huge number. Oh no, that's not bad at all. That's fine. All right. Even if you multiply that by 10. All right, I think we're okay. I think this is fine. Trying to think if there's a way to do this. It's a little bit faster in terms of, yeah, I guess you just brute force it. I don't think there's really another way to do this. I don't think it's intended to be another way for this as well. So we have const auto DFS. And we'll have const int I or a, int b, const auto f, and this actually doesn't return anything, believe it or not. We're going to DFS of 0 to the end, which is num.size. I actually don't know if we want that either. I'll explain. And the target we want also. So something here is the A to B. I don't know if you even need an A to B really. I think you just have an X or an A. Don't think you really do need one of these because you just go into the end every time. Okay. So the positions. So there's some base cases or base case. There's a recursion. The recursion we're going to say. So we say for each index int I equals a, I is less than num.size, increment I. Excuse me. So what we're going to say is we're going to say this number, the number to the left, we're going to initialize our number starting with the digit here. So we'll have int current equals 0. Current is equal to 10 times current plus num of I minus 0. That's the digit. So this current is some number. And we're going to have, and we also want a current value. Or yeah. Some other number. Well, I'm not sure if that even matters. Do we need that? Yeah, we just need the result. I don't think we actually need this number. We might not need it. This is actually going to return a couple of things. A tuple of two things. One is an int, a value, and the other is a vector of strings. Or it's going to be a vector of tuples of ints and strings. Yeah, it's kind of involved. Awkward, but okay, I think. A vector of tuples of ints and strings. So what we're going to do is we have a string that we return, so we can recurse on f. We don't have the base case here. What's going to happen is we create this number on the left side, and we're going to recurse on I plus 1. And how this is going to happen is the index A is where we start our number, and we can go left to right all the way down to the right, pretty much all the way at the end, and create that number. I have a question here actually about what's expected. Can we do, if we just had 10, 100, 100, what does 100, 100 give us? Wondering if 100, 100 will, okay, expected is 100. So the number itself could be equal to the target. So there's that as well. Okay, I'll keep that in mind. So we can go all the way down. And we're going going to say could return 0. So this is a little bit tricky. I want to include that if the number itself is already the target. That really would go here, though. We'll come back to the base case shortly. We'll say if current is equal to target, we can ret.pushback. Just standard string of target. This only works if I is 0 and part of A is 0 and I is yeah, we don't actually need to do that. We don't need to handle that case. That's really only if edge case. If just x equals 0, I equals 0, I is less than num size, 10 times x plus num of I minus 0, x equals target, then ret.pushback. Standard 2 string of target. Something like this. This should handle the last case correctly, the one that's 100 has 100. How are we doing on time? 17 minutes, 18 minutes? Alright, I'm kind of lowering my voice now because I think people are sleeping. So I'm going to raise my voice and start whispering so we can just whisper instead of keep my voice kind of low. So yeah, so we got the second one. That's what we just wanted to take that edge case. What we're gonna do though is we have an integer. We have 3 operations we're gonna process. So we can have. I mean, we could just do each operation one by one. That's fine. I don't need to go crazy here. We want. I'll have to get back to the base case in a minute, but basically, there is a vector auto. So what we're going to want to do is a result of operating on the right side with some amount. We want to get all the possible numbers and strings sort of top down. So all the possible numbers and strings we can create on the right side. And what we're going to do with that is for each of those, if adding current to that, whatever that is, allows us to get to the target, then we can update the string and we have a return value here. So we'll have our return value here. Actually, I think there is no base case ultimately. I don't know. Well, okay. So what we're going to do is for const auto, we're going to have val and string, these tuples in the result. We're going to say ret dot push back. So for each operation, we're going to say val is on the right side, so we're going to say current plus val times val minus val, and yeah, this is okay, we don't have to worry about division. And then we're going to take s, and we're going to add this character, so we're adding, and toString of current. So we'll have temp is just toString of current. Say temp plus this, and we'll do the same deal on every one of these. So we can do multiplication, addition, subtraction. Like we're basically just brute forcing this. And the result is we return ret. So for each integer we can make from left to right, we have a subroutine we can run on the right side, which gives us a vector of results and the strings that give us that result. And we're going to take each of those results and we're going to update the value and update the string and push that to our return vector. And that's what we do. Super simple. And then we're going to say the base case is if a is greater than or equal to num.size, then I think we return just an empty vector of tuples. I think it was just a tuple of an empty string, 0 and empty string. I think that's all you really need. Or maybe better would be if a is equal to num size minus 1, and this doesn't go all the way to the end, stops at the last number. You could say something like this, actually. The base case could just be when you get to the last number here, when you get all the way through, you can push that number into the return vector as well. So you don't really have a base case. And that actually handles this case too, by the way. Excuse me. Yeah. You can just return nothing. And then we can just say if a is equal or I is equal to num.size minus 1. And then we can just say ret pushback. You could do the base case here, or sort of a pseudo base case. Oh, there's also, you have to make these tuples. Forgot about that. And this will just be current and empty string. Oh no, I'm sorry, temp. So this will be on the right side. If you get all the way to the end, we could push that. That actually, current should be at the end here. And now you say auto result. There's probably a better way to do this, by the way. And we're going to say auto ret. Excuse me. For const auto v and s in the result. We can say if v equals target. And we don't really need the target, do we? We're not going to, there's no real pruning that we're going to be doing here. Just ret num. We don't even need ret anymore either. And we're going to say if that's the case, then ret dot push back the string. Something like this is what we want. Let's see if this compiles. 27 minutes in. Temp would be, oh, I see. Yeah, sure. This might be better. Yeah, you could build this string also, instead of calling the toString over and over again. I think that works. Oh wow, whoa. Nice. Nice. Very nice. Very nice. Oh. Ooh. Okay. So these need to be longs. Something like this, maybe. Wrong. Oh man, it's wrong. Whoa. Oh. Interesting. So one of the issues here is the precedence, right? The order of operations. Oh no. Oh no. Oh, this is so much harder. Oh no. Oh man. So part of the issue is if we multiply, so multiplication happens before any of the other operators do, which means yeah, these numbers are not correct. So if we evaluate this expression, so there's a couple things. One, we don't have the leading zeros are not correct. That's kind of awkward. Excuse me. So maybe it is better to just convert this each time to a string. Let's start with that. 260 milliseconds. Oh, that's so long. How slow was it before? It's an improvement on some of these. It's formatted correctly, looks like, on some of them. Yeah, it's not much better. Really that much, not much better. So now the question is, how do we handle the operator precedence? No, it's quite a bit better actually. It's quite a bit slower if we don't do it that way. So I think, you know, we can do. I think we can just say the statement if. By the way, we can take this character instead of calling this so many times. If C is not equal to 0, then we can, otherwise we don't add anything. How about that? Oh, actually, oh, wait. Wait a minute, what? This actually should be fine. This part is not the issue. The issue is that's not correct the way that this works. Oh, okay, well, there's that. We just have, we'll just put if statements. If temp is the empty string and C is equal to so say if temp is the empty string and C is this character, as long as this is not the case, then we temp plus equals C. This will get rid of the leading zeros, I think. Wait a minute. What? What? What did I do? Okay, this works. I mean, it's incorrect, but it works. So we say if, so we say character C, constant character C, num of I, and say if oh no, wait. So temp is not equal to the, so if temp is equal to the empty set and C is equal to this, and we don't, so we'll negate this. So negating this would be if it's not equal to the empty set or not equal to, yeah, so that's interesting. So as long as it's not a leading number, and if it is a leading number, it's not 0, then we can add it. Otherwise we don't add. Yeah, I got some compiler error before that. It was so strange. Also, whoa, look what happened here. I don't know, but another problem is actually if, oh no, it's wrong. So if, so it could have a 0, but if temp is 0, then you can't have, yeah, if temp is already a 0, it can't be a leading 0. So I guess what you do is you just say, do something like this. Okay. That gives us roughly what we're looking for. Oh, but there's another one here, 2 plus 6, 6 plus 2. So 2 plus, so my output, I'm missing 2 plus 3 times 2. Oh no! Is that because of this? So confused. It's taking a while. I wasn't expecting this to take so long. So we're actually missing one times 5. Hold on, what is so different? There are a few things that are wrong. So 6, 6, we got that right. This we're missing one altogether. I don't know how that happened. This one is, we have too many. 1 times 5. This should be not allowed, right? So actually, if it's so we have to use each digit. So actually, this case gets skipped altogether. So if temp is equal to a 0, then we actually break altogether, I think. Yeah, like it just breaks down altogether. pretty much just if, really this is the first first value, first index is a 0. What does this do? One times 0. How did that happen? What? Well, that's just bewildering. How did we get I mean, you can, what? You can have situations where 1 multiplied by 0. Where do we get that from? What? Huh. So this is 105, right? So what can happen is you can say 0, 5, 1 times 0, 5, but that won't work. So you can only have a 0 here, and then beyond that, we don't continue. We break on this. But why did we get But this should have just stopped here. Oh, that's because you make a tuple here and add it before return. So this is current temp, which is 0. So you get 1 times 0. I think that's why we got this one. Yeah. Just to make sure. This is a subtle thing. Basically, make sure you made it all the way through on your program. Oops. I think that's why. I think because we ended up adding 1 0 there. Oh wow. Whoa. That's confusing. This doesn't do what it was supposed to do. That's really confusing. What is going on here? Now nothing comes through? What? That is really confusing. What is going on? Isn't it supposed to? It's only supposed to add one thing. What is going on? Let's go to 1, 2, 3. Let's try to debug that. Okay, I'm lost now. I don't know what's happening. What happened here? So before, you would get all kinds of stuff in there. So my eyes here, my eyes aching. Okay, but what would be... Excuse me. Current 3, temp 3, current 23, temp 23, 3, 3, 1, 2, 3. So 3, 23, and 1, 2, 3. I is 3 in all cases. Oh, of course. Ah, that's why, because I gets incremented at the end. Oh, duh. Duh. If you terminate early, it won't be incremented. It'll be incremented, but you won't get to the end. I see. So here, once you've already processed this value, what's tricky about this though is, okay, I see what the problem was, or is. There's another issue here though. Yeah, I think you should decrement I to guarantee that you're not on the edge. You don't go over. So we're going to try to handle leading the zeros correctly here. And we still have to handle the order precedence, order of operations precedence. Alright, there we go. So now I don't have that 0, 5 in there anymore. Yep, only one thing that looks wrong. Okay, good. So now this is, oh no, there's still 2. We're still missing, we're missing this one. I don't know what happened there. So that's the second case, 2, 3, 2. So this I don't understand at all. What's happening here? We have 2, 3, 2. We have 2 times 2 plus 3 times 2, and 2 times 3 plus 2. Right, the reason is that this is order operations related. So the problem is that we're supposed to perform the multiplication before we perform the addition, which actually breaks the other solutions. So they don't have parentheses around them, so you could end up in a position where you can perform multiplications and it won't, so we can't do it this way, basically. Not basically, but in other words, in another sense, we can't actually take this approach because we can't assume that whatever we evaluate to the right is going to evaluate exactly the way we would like it to. What we can do is give us a count when we're multiplying from left to right of what the if we have sums and multiplications and I guess what I want to say is like we can maybe process things slightly differently such that our multiplication is handled correctly. Right, so if this was just addition and subtraction, obviously we would be fine because we perform our additions and subtractions the same precedence. What's interesting here is actually we're performing our operations right to left rather than left to right, which is also kind of weird. So you would expect issues with subtraction too, because subtraction has to be performed left to right, not right to left. In other words, we add 5 and 5, and then we add 2 and 2. So we do 6, 2, and 2. I think we'll have an issue. 6, 2, and 2, and I don't know, something like 6, 2, 2, and 0, 6, 2, 2, and 2. Something like this. I think we'll also have problems. So yeah, I didn't really involve operator precedence correctly here. Six times 2 minus 2 gives you 0. Yeah, well that's a multiplication issue. With this one, 6 minus 2 minus 2. Gives you 2. So we don't have that one. You see that? There's no 6 minus 2 minus 2. Because we perform the 2 minus 2 first. So actually there's another problem here. We're performing our operations from left to right instead of right to left. Which is awkward. Yeah, the parentheses should actually be on the left side, not on the right side. Oh, this is awkward. I think we're in trouble. I think we're in trouble. We have to rewrite something here. Uh-oh. Uh-oh. I didn't realize the precedence would be the main thing. I didn't really think about it. Uh-oh. May have to make this a part 1 and come back to it. I might do that. Processing from right to left. The problem with doing right to left is building the integers is a little more complicated. So right to left, what we can do is, excuse me, we would process the left side and then subtract the right side, or process the left side and then add the right side. So it's almost the same routine, but just in the other direction. And this allows us to have the parentheses will be on the left side. So I process the left to right in that way. what the problem you run into again is the multiplication. So multiplication has a higher precedence than either addition or subtraction. Excuse me. How do we enforce that while we're iterating? I mean, oh, my neck. So we can rewrite this to go right to left, but the problem we run into again is, excuse me, from right to left, the problem that we run into is the multiplication operations. If you did like 10 plus 2 times 3 plus 10, you would evaluate the entire left side before adding the 10 on the right, but the 10 on the left, you would not evaluate the 2 times 3 before you add the 10 and the 2. You would have, yeah, you'd have to, excuse me, yeah, before you multiply by 3, you'd evaluate 10 times 2 first. You can have a previous value previous product that you would multiply your multiplicand by. And the string would be built the same, but instead, when you multiply, instead of updating the value altogether, well, you can update the value altogether, but you're going to actually update the multiplicand, which is going to be the previous number, and add that. So you need to have the previous operation too, if it's multiplication or addition. It's kind of a lot of information we have to store. But you can do it that way. That works. It's really awkward to do it this way, but it works. You basically just keep track of the value that you're going to be multiplying, and then you don't perform the next operation quite yet. You only perform that operation towards the end, or you can perform that operation. Well, you only perform that operation, I guess, when you switch to something, another addition or subtraction. Then you update. Or when when you're evaluating at the end. So you can have these like partial states that you're working with. These tuples represent sort of partial states. It's super awkward. I think it works, but it's really awkward. That allows you to kind of inject precedence. Not inject precedence, but manipulate precedence. I think I'm gonna just make this a part 1 and come back to it later. I think we were already over an hour, and it's kind of awkward. I think it'll work, but there was something I wanted to see tonight. Could always see it later, but I wanted to watch it, most of it tonight. Alright, we'll just make this part 1. So yeah, we kind of goofed. Or I kind of goofed. Reading the problems is like the hardest part. Just understanding what they're asking can be so difficult. Just make it a part 1. Come back to it. All right. So thank you for watching. Talk to you soon. Have a good rest of your evening. And yeah, I think the problem is we just need to, instead of going left to right, go right to left. In the other direction, and then also we're going to manipulate things a little bit so that way we can process the multiplication portion. So we're going to have like sort of partial states going where we know what the previous operation was and the thing that we're multiplying by, or actually we're going right to left, so we would know if we're going top down from left to right, the right side is evaluated. We want to do top down, right to left, so the left side is evaluated. So we're actually going left to right. From top down, right to left. It's confusing, but yeah, the left to right recursion. We want sort of partial states where we know what the previous operation was, addition or subtraction, and what the sort of current product is. That's going to be added or subtracted. So there's a value of the operation and then sort of a product that's being built. And when you continue to add product values, then that state just kind of keeps iterating where you keep increasing the product portion. As soon as you switch to a plus or a minus, then you update the product portion and update the plus or minus operation, update the value. So you make all your updates when you actually perform an addition or subtraction. And at the end, you can just evaluate if you need to. You can. What that basically means is that at the end, the partial state, when you process, you're just going to perform the last operation that's required. At the end, you do that. You do that when you're processing, such that you can. Yeah, that way you can sort of always have that kind of, you kind of have that intermediate state that kind of grows as you move left to right. It's a little complicated. It's not that hard, not that confusing, but we're going to, yeah, I think the problem we might run into is it might be too slow, this algorithm. We're going to try it, but let's see how it goes. But yeah, thank you for watching. I will talk to you soon. Have a good rest of your day. And, oh, I'm sorry, there's one more thing we have to handle, which is the leading zeros. That also is going to be a little bit more awkward going the other direction, but that's okay. We'll figure it out. But yeah, I think sometime, maybe tomorrow, I'll take a look at this again. So yeah, thanks again for watching. Talk to you soon. Have a good rest of your night. And yeah, that'll be it for now.